May not know me, I am Giuseppe Longo, and I am the minority co-organizer of this meeting together with Nicolo, who did such a fantastic job in putting it all together. It's an honor for me to start the day, and without wasting any time, I just pass the words to our mayor, the Dr. De Magistris, who is the mayor of the town of Lecco.
Buongiorno, vi do il benvenuto mio personale e della città di Napoli. Ci tenevo molto a essere qui presente a darvi un saluto, soprattutto in occasione dei 70 anni del professor Massimo Capaccioli.
The mayor says that he is very happy to be here, and he came here to bring the greetings of the town to Massimo Capaccioli for his 70th birthday.
Ed è anche l'occasione per tributare il mio doveroso omaggio all'Osservatorio Astronomico di Napoli e a tutta l'astrofisica napoletana per quello che fa quotidianamente a livello italiano ed internazionale.
He also acknowledged the important role played by Napoleon and astrophysics in national and international scenario.
E anche tutto quello che appunto l'ex direttore dell'Osservatorio Astronomico ha fatto per l'astrofisica della nostra città, per la ricerca, e oggi possiamo dire sicuramente che l'Osservatorio di Napoli è una delle eccellenze mondiali e di questo siamo molto fieri ed orgogliosi.
He also wants to acknowledge the role played by Massimo Capaccioli in the growth of the Astronomical Observatory of Naples, who has become an important presence in the national scenario.
Recentemente abbiamo fatto tante iniziative qui all'osservatorio per ricordare quanto sia importante il contributo che la ricerca napoletana dà al progresso scientifico nel mondo, e quindi siamo contenti che si possa attraverso questo convegno internazionale divulgare sempre di più il ruolo di Napoli nel mondo, nella ricerca e nella scienza.
And he also says that recently, over the last few years, many different initiatives have taken place in this very same room, and all these initiatives were of very high profile and contributed to relaunch the image of the Astronomical Observatory of Naples and of Neapolitan science in Europe and in the world.
Quindi, come sindaco di Napoli, oltre che augurarvi il buon lavoro, vi auguro anche il benvenuto e una buona permanenza nella nostra città. Grazie.
And as a mayor of this town, he really wishes you good work, and he hopes that you will have a good stay in our magnificent city. Thank you. Okay, no, thank you very much. And now I give the speech to Professor Trombetti. I mean, he's the vice president of the local government of the Regione Campania, but for me, he is, and he always will be my former rector, therefore, Guido.
Thank you for your invitation. Grazie per il vostro invito, sono molto contento di essere qui stamattina, caro Peppe, per una molteplicità di fattori.
He is very happy to be here for many different reasons, which now is going to.
Sono stato preside della facoltà di scienze per circa 10 anni e ho avuto l'onore e il privilegio che il professore Capaccioli fosse uno dei più autorevoli docenti della mia facoltà. Sono stato lettore dell'Ateneo e ancora il professore Capaccioli era lì a dare lustro alla istituzione.
He is saying that he has been dean of the Faculty of Science of our university for many years when Massimo arrived in Naples and began to give his important contribution to science in Naples, and he has always been a rector for many years of our university. And during these years, Massimo continued to give his important contribution.
Ma il motivo sostanziale che mi rende felice stamattina è il rapporto di amicizia amicizia e di stima profondo ed antico che mi lega a Massimo Capaccioni.
But the main reason why he's happy to be here today is the very deep feeling of mutual friendship and mutual esteem which is between the two of them, between Massimo and me.
Massimo Capaccioni ha dato contributi fondamentali all'astrofisica internazionale e nazionale e a costruire una scuola napoletana, ma una caratteristica che mi piace ricordare, mi piace segnalare di Massimo Capaccioni è che lui è un uomo di cultura a tutto tondo, non è prigioniero di animi specialisti come ogni tanto ci capita di vedere, ma è una persona che spazia con la sua cultura veramente a 360 gradi.
Okay, I will try to translate. Long sentences make me difficult to translate because I forget what you said. And okay, he says one of the things which he likes about Massimo is that besides his scientific contribution, which are important and internationally known, he has always been, and will agree on this, a man of culture, so not only scientific but also humanistic, and it has always been very proficuous to interact with.
Quindi concludo questo mio breve intervento ringraziando Beppe Conco, tutti gli organizzatori, salutando tutto il personale e i ricercatori dell'Osservatorio Astronomico, che è un'istituzione di grande prestigio per la nostra città, per la nostra regione, e augurando a Massimo Capaccioni di continuare a condurre con piglio di qualità che lo caratterizza la vicenda culturale che lo ha visto protagonista in tanti anni.
So basically, he wishes to thank all the organizers of this meeting, and also he wishes that Massimo will continue giving his contribution to the culture of this town and this region. So, now I give the microphone to Professor Bonanno, who is also the president of the Italian Astronomical Society, who is co-sponsoring the meeting.
I am here as a president of the Italian Astronomical Society. Massimo Capaccioni, as most of you know, president of the society for almost 10 years. And it seems to me appropriate in this case to remind briefly the history of our society. When in 1871 the Italian troops arrived in Rome, which was still ruled by the Pope himself declared himself a prisoner of the Italian king of the epoch. The problem was that the most important astronomer of the epoch, as most of you know, was a Jesuit, and he couldn't acknowledge the newborn Italian reign. And the problem was that the Italian troops arrived in Rome in September, and the problem was that in December was expected an important solar eclipse in Sicily, which belonged to Italy, not to the Pope reign. So Angelo Secchi, as an astronomer, was willing to go to observe this important astronomical event, but he couldn't go because he didn't acknowledge the Italian reign. So the solution was to invent the Italian society. Italian in the sense that all the astronomers living in Italy, even if not at acknowledging the Italian rating, could belong to this new world society. This is this important tradition which Massimo Caraccioli received in his hands when he was the president of the society, and he revitalized the society with important astronomical events, with important publications, with important cultural events which he supported very much. I, being much younger than Caraccioli, of course, now I am the president, but I still have in my hand this tradition. I try to do my best in order to keep the society at the same level, and of course, I know that Massimo is still following closely the activities of the society. This seems to me an enormous merit. This is what I want to say today. Thanks.
Now the last introductory short speech from Gianni Pusarello, who is here as a delegate to the director of the Observatory, Massimo Della Valle.
Good morning. The director, Massimo Della Valle, unfortunately cannot be here this morning because of family problems. He sends his apologies and asked me to welcome you all this morning, and I am glad to do that. Let me first say that we at the Observatory are proud to host this meeting, addressing maybe the most effective method of investigation in modern astrophysics. Actually, large digital surveys allows us to enlarge our knowledge of the universe, of galaxies, including the one where we live in. But we are proud twice today because this conference is the occasion to celebrate the anniversary of Massimo Caraccioli and to account for his contribution to science. I think, but actually I believe that Massimo agrees that this is the proper way to celebrate him, talking about science surveys. I thank the authorities, either political or academic, who are present here in support of this meeting. I wish you a pleasant stay at the observatory, a pleasant stay in Naples, and let's have a fruitful meeting. Now I give the floor to Nicola Napolitano.
Hi everyone, I hope this is not going to be the longer talk in the welcome speech. But okay, so welcome to the Universal Digital Sky Service, jointly organized by the Department of Physics and the University of Federico II and the INAF Observatory of Capodimonte. So I guess that everybody is really excited to start this conference and hear and see what is going on outside the universe. But before, and all the scientists from around the world are deploying immense efforts in technology and science to understand better what the universe we live in, and in particular the dark sector, dark matter and dark energy. But before we start, I have to thank some people who made all this possible. First, I'd like to thank every single person of you. There are people who stepped outside their office to be here, and people who traveled outward. I got to say that all of you have been, with your enthusiasm and your questions and requests, motivating all of us to make this conference the best for all of you. Who is us? Us is the local organizing committee. Of course, the people of the Capodimonte Observatory and the Department of Physics who worked hard in the last months to have this conference today. I'm truly thankful for the work they've done. I also have to thank all the sponsors that have supported either morally or economically the conference, and that you can find on the website. But a special thanks goes to the Institute of National Astrophysics, INAF, which is the national research facilities that it includes all the Italian observatories, which strongly supported the conference, and the president will be also visiting us tomorrow. And but another special thank goes to ESO, the European Southern Observatory, which exceptionally has sponsored this conference to witness the special liaison with the Observatory of Capodimonte for the work done together, in particular throughout the BST telescope working in Panorama. I have to thank also the local government. We had a representative here in Naples, and so the mayor and Professor Tringetti, which have always demonstrated and showed interest in research within Naples, as they said. And I also want to thank all the team, the university, and the department, which accepted to be part of the committee, including the University of Naples, Partenope, University of Salerno, University of, but also the University of Lomosmo of Moscow, and the university. And all the presidents and all the major academies located here in Naples. But my deep and truly thank is for what I call the Dream Team, the scientific organizing committee. I call Dream Team because when Giuseppe Longo and I started to put this conference together, we could not imagine such an enthusiastic response from all people invited to join the committee. And you've been really inspiring during all the conference preparation and very kind to accept to be here. I'm sure that if we have all this crowd here, is because your names are on that list of that poster, and also because of the list of all the invited speakers that, like you, have accepted to come to this conference with no financial support. Thanks to all of you. I conclude this very long thank you list with this tiny person over here, Massimo Capaccioli. I guess that if he didn't turn 70s, we wouldn't have probably a conference like this today. Well, Massimo did many other things for the Naples and for all the world, many other things that other people better than me will talk to you about in the university conference. But let me say for the moment that yes, he has to turn 70s more often in order to have more and more conferences like this and more beautiful people like you attending. So thank you, Massimo, and thank you all. I think we can start the talks, and the chairman of the first session will be Professor Ken Freeman of the Australian National University. I give you the word.
Well, it's a great pleasure to welcome you all to this first scientific session. Massimo and I have known each other since shortly after the Big Bang. It's a special pleasure. It's a special pleasure to be here and to chair this first session. So our speaker is going to be Tom Shakes, who will speak about digital sky surveys from the ground, status and perspectives.
Thank you, Ken. Can everybody hear me if I just shout?
You can close it.
So what I'm going to try and talk about is ground-based digital sky surveys. I'm certainly going to give you the status, but I'm not so sure if I'm going to give you the perspectives, but we'll try. So of course, the focus, have you got a pointer?
Pointer, yes.
No, it's okay. It's okay. So of course up here we have what we'll call for today Capaccioli's VST, and down here is the Vista Survey Telescope, and these will also be featuring strongly in my presentation. So I've tried to make a list of recent optical and near-infrared digital surveys, and you get quite a long list, and many of those surveys will be talked about at this meeting. So, of course, the prime one was the Sloan Digital Sky Survey, which was a success, still going on at the present day. It has been the sort of flagship for many of these surveys, hoping for the same success in the future. So what I'm going to do, I can't possibly go through all these, and I say many of these Surveys will be talked about later in the conference anyway. WISE, I'm going to talk about in passing. Of course, it's not a ground-based survey, but it's a satellite survey and near-infrared survey. But it complements so well the rest of the surveys I'm going to talk about. I've included it here. These arrowed ones are the ones I'm going to be focusing on. Pan-STARRS isn't talked about much in the rest of the conference, so that is a focus for this review. I want to also talk about ATLAS and KIDS, the two VLT survey telescope. Capaccioli's VST is what we're going to be calling it, as I said. And these are the two surveys I'll be talking about from VST. Of course, there are other surveys. There are galactic plane surveys and VPAS and others. And again, they will be talked about. So the bias here is towards extragalactic surveys more than 100 square degrees. And so that's why some of the galactic plane and so on surveys are not mentioned here. Then the two near-infrared surveys, the VISTA, VHS, and Viking, I'll try to get through, and not forgetting the dark energy DES, which Manda Banerjee will be talking about later in the conference. So you might see this picture again, but this is IAU 78. This actually was to prevent George Torgosky saying, complaining that I've forgotten about the Schmidt photographic surveys that went in the 20th century before the digital surveys, the digitized surveys they were, not the digital surveys. And so this is, I was actually at this conference in September 1983, astronomy with Schmidt type telescopes. Thankfully, I can't find my own picture in this crowd of people, but I think Massimo, is that you up there? That is Massimo. He was, of course, the chief organizer for this conference. And again, a lot of the talks that you're going to hear today are going to be paying tributes to him. So this is one of the. So what I'm going to start with is the ESO optical and near-infrared surveys. And this is the VLT survey telescope that Capodimonte and Massimo had such a big hand in building. So this is the telescope here, 2.6 meter. The Omega Cam camera at the back. And this is the telescope that is used for the ATLAS and for the KIDS survey, the kilodegree square survey. And so here are we're going into the ESO surveys now. This is the footprint of the ESO surveys. The red areas are the VST ATLAS, sort of southern Sloan, covering something like 4,700 square degrees in the southern and the northern galactic hemispheres. There's also the KIDS surveys in the green, covering something like 1,500 square degrees between the two northern and southern areas. And then the purple is the VISTA Hemisphere survey, which is a near-infrared survey, which is a complement to ATLAS and also to DES in terms of near-infrared. So again, starting with ATLAS, it was envisaged as being a southern Sloan, covering something like 5,000 square degrees of the SAE. Its bands are the same as the Sloan bands, and it was envisaged as getting to the same depth as Sloan. So this was UGRIZ with something like 100-second exposures, and also with the Y, J, and K bands being supplied by the VISTA Hemisphere survey. The pixel size for the Omega Cam camera is 0.2 arc seconds. That's half the size of the Sloan pixels, and that accounts for the slightly longer exposures to get over readout noise. But this 0.2 arc second pixel size has the benefit in terms of the seeing that we get from the VST, as we'll be seeing in a minute. This all amounts to a 1 degree by 1 degree field for the telescope, and ATLAS so far has observed something like 3,500 square degrees, and there's been 2 data releases, 1,500 square degrees released in DR1, and 2,500 square degrees about to be released in DR2. So again, the ATLAS science goals were cosmological mainly. We've already done a 10,000 quasar redshift survey, completed using the Anglo-Australian 2 degree field instrument. And this is maybe a pilot now for a larger survey with complementing the eRosita X-ray telescope that will ultimately fly in observing the X-ray bands, and also possibly followed up with the foremost spectrograph when that replaces the infrared imager on VISTA. So we're trying to cross-correlate ATLAS with the microwave background to test the accelerating universe via the correlations that are expected in an accelerating case with luminous red galaxies. We also want to do quasar lensing with photometric redshifts through this UGRI, Z, YGK band passes. We also do galaxy counts to study the extent of local inhomogeneities like the local underdensity that people have talked about previously from the photographic survey. So also other sorts of science that these sort of surveys do, high redshift quasars. We cover the great attractor region, fornax, and other clusters, and we also sensitive to looking for Milky Way satellite galaxies and stellar streams. So this is the sort of status of the ATLAS at the minute. Of course, the reason for slightly overdoing it on the ATLAS is that, say, there's no talk to come on ATLAS, so this is the ATLAS, from the ATLAS talk you're going to get. So this is the sort of southern galactic cap and northern galactic cap. So as I say, something like 3,500 square degrees, something like 3/4 finished, slightly more in this infrared band than in the UG and R band. So in about 6 months to a year, we'll have completed all of the ATLAS in GRI and Z. It'll maybe take a little bit longer to complete it in U. The magnitude limits we get to are slightly fainter. These are the sort of distributions of the magnitude limits in each of our tiles that we've taken already. And so we're getting to something like G of 23 in the G band, 22.2 in the R band, 20.1 in Z. These are all something like a few tenths fainter than the equivalent Sloan limits, which was our purpose in terms of our first scientific specification, was to get at least as deep as Sloan. And it's a little bit, maybe half a magnitude deeper in the Z band. But the really interesting thing for Capaccioli and for the VST was the seeing distributions that we're getting out. Whereas Sloan median seeings are something like in the range 1.4 to 1.6 arc second. It's Apache Point site in the USA. Here, even in the U band, their median seeing is something like 1 arc second. In the G, it's 0.95 arc second. In the R, and remember the kids survey takes our best seeing at the VST, but even once you've taken that out, the R band seeing median that we're getting is something like 0.9 arc seconds. In fact, the PI of kids, Conrad Koiken, he's slightly worried that we've been getting better seeing than we should have been, but anyway, it's all the benefit of the ATLAS. And of course, in the I and Z bands, it's even better, where there's less competition from kids. 0.81 arc second median and 0.84, and the distribution is going down to half an arc second or so at its best. So what you may remember is the issues that VST has had in the past with the mirror and the breaking of the mirror and the accidental images. So I find it particularly, powerful that you can see what the quality of images that the VST in that mirror is now producing, and it's a wonderful tribute to Massimo and his persistence with this project. So for instance, you look at actual images, and what you see here are two redshift 0.24 clusters. They weren't particularly hand-picked, they just happened to be in the overlap region, the slight overlap region we have at the equator with Sloan. These are two redshift 0.24 clusters, and when you look at the SDSS version of this picture in the I band, it's the seeing, it's 1.2 arc seconds full width half maximum, whereas the VST ATLAS image in I is actually 0.62 arc seconds. So you've got to keep remembering there are 4 times as many VST pixels on this side of the slide than there is SDSS pixels on the far side. So again, you see these same two clusters now moved down a bit, but this is this one here in the ATLAS picture. This is this one in the infrared from the VISTA hemisphere survey from the VISTA telescope. And again, you see again 0.73 arc seconds at K, but VST actually beating it, as I say, 0.62. You also see here, so this cluster here is the same as given in the Y satellite, but much worse. seeing or point spread function at 3.4 microns, big and blobby in the infrared, but you can see how well these luminous red galaxies, if you like, are coming through in the WISE data. And what you also see up here is a redshift 1.34 quasar coming through both very well in the Atlas and in the Vista picture, the K-band image from Vista. But also you see that here in the WISE image, and this is just emphasizing what a wonderful partner and how appropriately matched is the depth of the WISE satellite images with the Atlas image, the VST Atlas images that we're getting. And of course the Atlas resolution is many times, 10 times better in this case, but it's a wonderful complement, this resolution in Atlas and this sort of depth in the WISE data. So again, with this sort of seeing, I'm not saying you get sub-arc second seeing all the time, but in most of the fields you can find images that at least are sub-arc second. So Paul Schechter, for instance, he wants to find quadruple lenses in the Atlas data. And so what you see here are actually 3 lenses that he found earlier, not from Atlas, but from other surveys. But these come up, these are overlapping our Atlas region. And here, so these are just only 3 that overlap. And here you find a 0.64 arc second image in Z, quadruple lens. Not quite resolved, you can still tell it's not a point source, but it's extended. Another quadruple lens from Schechter, 0.6 arc second seeing in the Atlas R band, and this one 0.91 arc second, not so good, but still always sub-arc second. You can still quietly see the sub-arc second quadruple quasar lens resolved by VST. So here's something else that we've been looking at. We haven't found any particular arcs by ourselves yet, but again, these are big galaxy, rich galaxy clusters. This one at redshift 0.3-ish, Abell 2667, which has got a famous HST arc in it. This is a lens galaxy now around the quasar behind the rich galaxy cluster in the foreground, and the rich galaxy in the cluster in the foreground is lensing the background galaxy and causing it to smear out into an arc. Now, I didn't hesitate to show you the HST picture because it's hard to compete with HST, but in my younger days, you would have to go to the Space Telescope to see arcs like this. But the fantastic seeing we're getting at VST and the depth of that is combined with, we're seeing this arc here, we see another arc up and down here, and this other low redshift cluster, but with a background galaxy. Here, RCS 0327, the Red Sequence Cluster Survey. You'll be hearing more about that later in the conference, that survey. But here's one of the arcs that they found previously in the south, and quite clearly seeing it in the 0.65 arc second C in this case from Atlas, and this is another arc that was found in the Sloan this time. So I'm not saying you can't find these things in Sloan, but this sort of seeing that we have in the VST Atlas certainly helps you to pick these sort of objects up. And of course, what we're trying to do is look for more of these new examples that haven't been found before, but we will find in Atlas. So again, this is the highest redshift cluster that we've so far been able to find. This is a Planck cluster that's detected by Planck with the Sunyaev-Zel'dovich effect at redshift 0.72. It's this S-shaped thing that you see in the Atlas. It's now 1 arc second, it's a 0.73 arc second Z-band image, but I chose to show you the I-band image for clarity. And here is the same image in Atlas. Again, these very red galaxies coming in very powerfully in the infrared bands, and that coupled with a high resolution that you see in the optical is a powerful combination for picking up not just clusters, but luminous red galaxies right throughout the Atlas survey. So again, those of you who know quasar selection, this is a typical optical quasar. This is actually from Atlas itself, U minus G versus G minus R. This is the stellar locus here. These are the quasars coded by the redshift in this part here, very close to the stars. So this is one of the things we can do with Atlas with its ultraviolet coverage, is select quasars in a reasonably efficient manner. But look at this in the now including the Y's 3.4 micron band along with the I minus W1 color against G minus I. Again, this is the stellar locus, but now this is the movement between the quasars up here and the stars down here, much bigger gap than you would see even in the traditional ultraviolet excess. So this is infrared excess that you're seeing here from the quasars non-thermal spectrum compared to the thermal spectrum of the star, similar to the ultraviolet excess at the other end of the spectrum that you see in the optical. And we've used both these combinations to pick out quasars, which we then went to the Anglo-Australian Telescope 2-degree field instrument to observe spectroscopically. And we actually, these are just examples, we got 10,000 quasar redshifts already from that route, based on Atlas and to some extent on WISE as well. So of course you can use Atlas for other things. Here is a dwarf satellite galaxy of the Milky Way, which Belakourov, Mike Irwin's group at Cambridge picked up. This is somewhere between a protoglobular cluster and a dwarf galaxy in the crater constellation in the south, which is one thing they picked up. And here is another one that was picked up, a stellar stream that you see that other surveys, such as Pan-STARRS, for example, had missed previously in the, so a cold stellar stream picked up in the Atlas data in the Sculptor. So this was the workshop we had in Durham in April. Massimo was there, along with Paul Schechter and various others. Roberto Radi here, clearly saying something like, "This, wow, this data looks good, Tom. Why can I get my hands on some?" I think is what he's saying. So that was the end of the Atlas part. That would take us to kids. And again, this was at the Durham Review in April, and this is basically plagiarized Konrad Koikken's slides to give the kids section at the top. So as I said, it's 1500 square degrees, UGRI coming from the VST, ZY, JHK coming from infrared Viking and Vista. Median redshift something like 0.7, optimized for weak lensing, tomography, so gravitational lensing, weak lensing is its speciality, and where the band they use for the lensing, which you need the highest resolution, is from the R band, where they have 0.7 arc-second seeing, and then they get photometric redshifts, which you also need to help the weak lensing from these wide multi-waveband information you have from the optical near infrared. So this survey, as I said, exploits the VST imaging capability to its limit, and it's scheduled to match the seeing distribution. So when the seeing is good, they observe in R, when it's not so good, they observe in the other band. Or they do Atlas. So here you see the crucial R band. This is UG and R and I from this is the limits, exposure times, and the limits they're getting to, and then ZY, JH, and K are coming from essentially Viking, the infrared Vista survey. And so here you see this the target 0.7 arc-second seeing to a limit of something like 25.2 in the R band. Are they achieving it? We'll see in a second. This is how they've gone in terms of completeness. They're more complete in the I band. The R band is going a bit slower because of the need to get good seeing. But when they get with conditions, they certainly get the good seeing. You see the median here, something like 0.7 arc-seconds, tailing off as you get up even just to 1 arc-second, which is outside then their specification. Almost as good in G, a little bit worse in U, but still sub-arc-second in U and in I. So again, a classical tribute to Capaccioli and VST in terms of this 0.5 arc-second seeing that they're achieving quite regularly. Lensing success does not just depend, as Yannick Mellier will tell you, does not just depend on the seeing. You have to have consistent image quality across the field. Conrad claims that VST is unique for lensing work, at least ground-based lensing work. And this is the ellipticity, that is distance from the center for the optical axis, and you see a very small gradient. All the images are essentially round as you go from the very center to the very edge. And this is Conrad from the Durham workshop in April. So that's kids, and then I want another one I want to focus on in terms of optical survey is pan-stars, because we don't hear much about that. Pan-stars is done in Hawaii from a 1.8 meter telescope with 7 square degrees field of view. This is again from plagiarized from Stephen Smart's talk earlier in the year. So this is quite a massive and an ambitious survey. This is at 3 pi, so it covers 3/4 of the whole sky down to minus 30 degrees in the southern celestial hemisphere, which is this hole you see here. But this is composed of, the rest of this is composed of pan-stars images from all over the 3 pi region. So that covers the Sloan area. It also covers a substantial part of the Atlas area. It's also not so good in the U band. It doesn't do U at all. It's not that competitive in G, but in I and Z, it is highly competitive. It also does Y. It gets the limits something like 23.2 in I, so something like a magnitude past Atlas in I, and something like a magnitude and a half past Atlas in Z. And these are getting up for kids and for DES actually limits. Seeing isn't quite so good from its heliacular sight, 1.1 arcseconds generally, but still an impressive achievement. So this is actually showing you what you can do with pan-stars. This is an Atlas R image that I showed before, where you saw the arc. You can also see the arc in pan-stars as well, but it's not quite as clear, or it's given that it's supposed to be half magnitude or magnitude deeper in the R band. So that's telling you that pan-stars is quite variable in its depth across the sky in terms of the 3 pi survey. That's one of the limitations. If you're lucky, you can hit on a thing and still detect the arc. If you're unlucky, the seeing or the depth is not quite as good as it is in other places. So this is that S-shaped redshift 0.72 cluster again. So what you see is it's not as well detected in the pan-stars band, Z band, as it is in Atlas. But you also see these artifacts that comes from the way that the pan-star survey is built up from many scans across all of this area, and some at least accidental artifacts in the area. So it's not a survey you would like to use, for instance, to do very sensitive galaxy clustering to very faint limits. But again, if you're looking just for the odd object, the depth is still quite impressive in the redder bands. And so combining Atlas with pan-stars, you can still possibly make a good job of trying to detect high redshift quasars, or check if there's a detection in the pan-stars I and Z bands of a high redshift quasar that you can detect in Ys or in just the hemisphere survey and so on. So that's trying to give you some sort of picture of what pan-stars can do relative to the ESO surveys, Atlas and KIBS. Of course, the big beast in the jungle is the dark energy survey. This is a talk given by Ofer Lahab a few months ago. This is the DECAM 2-degree field. It's the same size as the AET 2DF instrument, but devoted entirely to imaging, just as the Anglo-Australian telescope camera is devoted entirely to spectroscopy. So this is on the Blanco 4.2 meter telescope, and it's showing that it too can pick up galaxy clusters, some of which are arced in the survey of, these will probably have been picked up by South Pole Telescope SZ data in the area below the Atlas survey. So Atlas is somewhere in here at the minute. This is the this is the DES footprint from year 1, which finished sometime earlier this year, in January, February, presumably. And they did this amount, at least partial covering of footprint in that time. So it's moving fast, as the outline is what they are planning to do. So ultimately they will cover both the Atlas and the KIDS area. So what can you do with DES? Well, DES also has reasonably good seeing. So we'll come back to this later. What you see is the full width, median full width half maximum seeing again is 0.94 arcseconds, and the RIZ filters a bit worse than the G and Y filters. So their spec is 0.9 arcseconds to do their weak lensing. But what you also see is this very steep drop down here at 0.7 arcseconds, where they're not getting any better seeing than something like 0.7. And we'll come back to compare that with KIDS in a minute. But you can see the quality images they're getting. Manda Banerjee will talk about this in more detail in her talk later in the week. This is a Space Telescope image of a cluster, RSJ 2248, showing again lens arcs, which you also see in the DES image. So I've only got a few minutes left. I'm going to quickly zip through in this review of ground-based surveys what the VISTA telescope is doing. Jim Emerson will be talking about these surveys, so I'm only going to spend a minute or two on each. VISTA, of course, 4.2 meter telescope. Jim will remind us what the field of view is, something like 3 square degrees, is it, Jim?
1.65 diameter, and each tile is 1.5 square degrees.
Right. So, powerful 4.1 meter telescope, again on the Panal, in the Panal observatory area. This is how far, so green is how far the VISTA Hemisphere survey has got. This was actually hasn't been updated since April 2014. I looked for it on the website, they still haven't updated it since then. The green shows you how VISTA Hemisphere survey is getting on. So Atlas is somewhere up in this region here, in the northern galactic cap, and then in this region down here, down to -40 in the southern galactic cap. Red is the Viking survey, which goes deeper as the complement of the KIDS surveys in the NGC area and in the South Galactic Cap area. So Viking making good progress again, as is VHS, and will probably have progressed on since here. Jim will tell you it's up to update its progress in his talk. So again, this is just a quick selection. I could have shown you high redshift quasars. I'm choosing to show you high redshift clusters. Of course, in infrared, you can go to higher redshift with a red object. This is again from South Pole Telescope detections of clusters. This one is redshift 0.76 now. Seen at 18.9 in the K band. And again, another cluster now seen at redshift 1.06. And again, seen at something like 18.5 again in K. So I'm afraid that was it for VHS. Jim will finish that off in his talk later in the week. Viking, this is from Alistair Edge at Viking PI. And so this is actually photometric redshifts, emphasizing what you can do with a combination of optical photometry from KIDS and the JHK from Viking. So this was actually from Koiken's talk, and what they're showing you is simulations for photometric redshifts from both simulation and actually from the data. And the claim is that they're approaching the theoretical limiting accuracy in terms of the photometric redshifts you can get in UGRI, Y, J, and K. And here again, some redshift 6 quasars that the Viking survey has already picked up. And this is from the Venemans et al. Collaboration, again looking for dropouts in the optical bands from KIDS in this case, and then detecting them in the infrared, as you see here, spectroscopically. So I'm just going to summarize now. And this, if you like, the theme of this talk, this is more the perspectives part, I'm afraid, than the status. But this is to sort of say, how desperate should you be if it happens that your institute doesn't have any access to the dark energy survey? And the message is, don't panic, because the ESA surveys are public, becoming increasingly public, and there's also the WISE data that's publicly available in the even longer wavelengths than VISTA Hemisphere survey and Viking. So the sort of things you can do, you can still use luminous red galaxies and emission line galaxies to redshift the 1. Of course, having optical surveys, very faint, just to pick up high redshift galaxies is not that interesting, because the L-type galaxies in particular drop out of optical bands quite early. So that's why there's so much interest in the infrared bands. But luminous red galaxies and emission line galaxies, as we ourselves have exploited and slowing out to redshift 1, you can certainly do with Atlas. And to some extent, it's pointless going fainter. When you get to a certain point with the luminous red galaxies, you are just you've got all the signal out in terms of clustering that you can get at some relatively bright magnitude, and then going fainter in that case doesn't improve your signal to noise on your galaxy clustering anymore. So in a way, this is why Sloan has been so successful in this redshift 1 region, and that's what you're still hoping to do in terms of Atlas, for instance, in the future. You can still do ultraviolet excess. You can still select quasars for redshift 3, ultraviolet excess from Atlas, for instance, and near-infrared excess from WISE. You can also do high redshift quasars, as I'm trying to explain. You always need the infrared bands, but you can combine the clean nature of the Atlas data in terms of lack of artifacts and cosmetic defects with the depth in the infrared, the I and Z bands from Pan-STARRS, Pan-STARRS 1 survey, and this makes a good combination for doing high redshift quasars. As you've seen, you can also get to the Milky Way southern satellites first if you have a clean, photometrically complete survey like Atlas. And Mike Irwin's group has shown how well they've done in that in terms of detecting that crater dwarf and that cold stream that we saw earlier. You can't do redshift 3 Lyman break galaxies, which I still think is a gap in the whole sky survey. You certainly can't do them with Atlas. You can't do them from because you need to get to U of 25 and a half to do UV dropouts at redshift 3. You can console yourself then that you can't do that with DES either because the UV band doesn't get you quite that deep to do Lyman break galaxies at redshift 3 either. The weak lensing is what KIDS depends on, and KIDS plus Viking giving you the photometric redshifts. You also need to do prosecute the weak lensing agenda. So again, this is Conrad Koiken, so don't blame me if you're a DES fan. But this is DES statistics in their first year of operation. Don't worry about this one. This is when the mirror temperature is higher than the dome temperature, then they get poor seeing all around at DES. But more normally, they get this sort of distribution. And what you see is, again, this very sharp cutoff between 0.7 and 0.8. So you're getting some sort of mode at 0.9 nanoseconds as they climb. Medium they claim is 0.94, but then a very sharp drop off from the short waveband side, short distance side, and they're not getting anywhere near the half-arc second that KIDS is getting. So this was Conrad's, I think, slightly biased version of this slide. He said this was the KIDS R-band distribution that I showed earlier from his DR2 data, and this is where he said DES was, and that sort of starts at 0.85. I think that's slightly pessimistic in terms of, so as a fair and unbiased reviewer that I am, I think that the arrow should go from somewhere here, but he still has a point that DES are in this range and KIDS R-band is in this range. And again, it's a tribute to the VST image quality of that Capaccioli and the Capodimonte team have generated. And so that's my summary. The chairman's looking nervous. Universal Digital Sky Surveys is both expanding and accelerating. There's one message that I hope you get from this rather brief review. Capaccioli's VST is working well. That's another, particularly in terms of its image quality. The ESO optical and near-infrared surveys plus DES mean that the southern hemisphere now has deeper imaging and more passbands than the north. It's another thing that's happening. I hope I've emphasized how the great complementarity of the WISE satellite near-infrared telescope with Atlas and VHS. Weak lensing, you can take your pick. The KIDS, a lot of that is publicly available, and DES will be at some point in the future. LSST is going to be spoken about somewhere else in the conference, and that's also now on the horizon. And in terms of perspective, the main issue for wide field surveys, in my opinion now, but it's not in the LSST people's view. They think that you don't need spectroscopy to follow up. You can do all that from photometric redshifts. I still think that spectroscopic follow-up is good. And if you don't not to have access to an Anglo-Australian telescope's 2-degree field, which is the prime spectroscopic follow-up in the southern hemisphere at the minute, you then have to wait for foremost on the Vista telescope and or DESI from Kitt Peak in the north. And so that's the choice you have at the minute in terms of spectroscopic follow-up. You can also use, of course, the VLT for your high redshift quasars and other things. But anyway, I'm beginning to ramble, so I think I better stop there. Thank you very much for listening.
We have time for a few questions, comments.
I guess I could just ask a question of how much spectroscopic follow-up do you need to cover the entire area, or is a portion like that provided by gamma sufficient?
Gamma is certainly an important aspect of the Viking, all the surveys, actually, ESO surveys, because of its, you have 23,000, I think, in the southern area alone, redshift, so it's an absolutely important thing. But of course, we wanted to do 300,000 quasars, not just 10,000 in the AET, to compete with things like EBOS. We think we've got the photometry in the UV and in the infrared to do that, and it's frustrating that we can't get on the telescope, competing with very good projects, of course, like Gamma and SAMI and all the others. But it's still frustrating, and foremost, of course, might be able to solve that problem. So we'd like to do bigger surveys of the whole area, and that was part of the vision for Atlas, for instance, in the first instance.
Daniel?
Maybe you've said it, Mr. Can you just maybe say again the overlap between kids and dads, how large that is, and also how do they compare that? So
well, it used to be 750 square degrees, which is the southern kids strip, but now, of course, decals is heading north on the other side of the sky, so it's now there will be complete overlap, 1,500 square degrees between both surveys. Ultimately, when decals and the legacy survey from DECAM gets going, and coupled with DES. But of course, for weak lensing, that might not be a bad thing, because the comparison between the two surveys may produce much more than either of them individually in separate areas.
And depth-wise?
Depth-wise, I would say they're both, I quoted 25.2 in the R band for both an AB system, from both DES, not DECAL, but DES, and from kids.
Okay, any more questions? Okay, well, thank you very much. Our next talk is the future of optical surveys from space and Euclid.
Give you a warning at 5 minutes.
Yeah, okay. Okay, good morning. So we'll move on from the ground-based surveys to space missions, and I will focus on the optical surveys, and by optical I mean UV, optical visible, and near infrared. I mean below 2 micron. So. Okay, so the motivation for that is why should we go for space for these next generation surveys? I think there are really many issues there which are most important that have been addressed already by Tom. The first one is the image quality, and the goal is really to move on to wide field surveys covering the whole sky or almost the whole sky with HST image quality. And that's really the future now for the next generation surveys, what we have in mind. This is also important for gravitational lensing, as you mentioned, but also for galaxy clustering and also high redshift galaxies or high redshift quasars. So that's definitely a goal, and this is a goal not only for morphometry and photometry, but also for astrometry. And so the image quality and the PSF is of key importance for the next generation surveys. The second point is probably the fact that near infrared and UV, of course, this is a way to go. It's really definitely to go to space. And the idea here is not only to go to space for getting UV and near infrared data, but also to keep the image quality as equal as HST data in this wavelength range. And this is why it is also important to think these surveys in the near infrared and near UV, and not only the pure optical, visible bands. Then the third point is definitely the image quality. And the image quality is also important for those surveys for calibration purpose and homogeneity of the surveys. You have no clouds, of course. You have stable PSF, stable photometric calibration, and stable astrometric calibration because of the sampling and the PSF stability. So here you win on all aspects of these surveys when you think broad surveys covering the whole sky almost. And then the last point is the data flow, of course. We can now, because of the resources we have, we can think about the whole sky survey with a sampling and a PSF of HST data. That means we are thinking about 100 to 1,000 petabytes of data. And we have now the resources, or we will have in 10 years from now, to do that. So the next generation surveys will also benefit from the strong improvements of the computing resources and the software we have and we are going to develop in the future. Okay, so, and I think that's plot here shows where is the revolution for the future. This is, the increasing total field of view covered by HST in 15 years, And this is the field of view that will be covered by Euclid in 1 year, okay? So you see that we are going to move to something less than 10 square degrees in 15 years, in 10,000 square degrees in 1 year with the image quality and the sampling of HST. So this is a real revolution that we are waiting for with Euclid, with W first, and possibly with Castor if we have this telescope developed by Canada in the future. So the three examples I'm going to show here, of course I will insist on Euclid for quite obvious reason, of course, but I will also argue that W first and Castor are really excellent prospect for the future of this broadband wide field imagery capability for all sky surveys of the future. So let's first start with Euclid and W first. And these are two telescopes have two important strong motivations based on two major discoveries. The first one is obviously the accelerating expansion of the universe that we know, from HST, but also from from Taponet supernovae, but also from baryon acoustic oscillations and other surveys, that this is definitely demonstrated that the universe is accelerating. And it is now dominated by an unknown component that represents about 70% of the total matter energy of the universe. So added to the dark matter itself, it represents 95% of the component of this universe. And none of them, the dark matter and dark energy, are known so far. So there are definitely here fundamental questions for physics to be solved in the future. And this is why telescopes like Euclid or W first are going to be developed. And the goal of this satellite is really to understand the very nature of this dark energy component and whether it comes from a pure, a real new field that could be associated to a dark energy, or whether it is something related to modified gravity, in particular on cosmological scale, where general relativity could no longer be valid when we are exploring the very large scale structure of the universe. So these surveys really want to explore the universe, the geometry of the universe and the cosmic history of the structure formations in order to understand what is the very nature of dark energy. The second point, the second major discovery is the fact that we know now from Kepler and many other surveys that we expect billions of solar systems in the universe. And these billions of solar systems, which are now up to going to a level of industry, are going to be explored at a very massive level with next generation surveys like those that could start W first, for instance. So as for Euclid, or W first, that will focus on dark energy on one hand, they will also focus in particular, W first, on the exploration and the understanding of this new system, new Earth, new habitable zone systems. They're characterizing their properties and characterizing also the solar systems and the stars that could generate this planetary formation going to Earth-like system. And W30 is really, in this respect, most fascinating telescope for the future. Now, Euclid itself is a telescope which is really designed for dark energy. And the goal of this mission is to use, on one hand, gravitational lensing and weak lensing tomography in order to slice the dark matter power spectrum as function of redshift and see how the dark matter power spectrum evolves with redshift. These surveys will explore the 10 last billion years in 10 slices in order to see how dark energy and dark matter impact on the formation of larger structure in the universe. On the other hand, Euclid will also have a spectroscopic facility, a slitless spectrograph, in order to get millions of redshift, about 30 to 50 million redshift. First of all, to use baryon acoustic oscillations in order to explore property of dark energy as well, and also redshift space distortions in order to decouple what could come from dark energy or modified gravity. And this is a coupling of the three probes that will provide enough information as function of look-back time in order to uncover the real nature of dark energy in the universe. So one key question with Euclid is the fact that because you are using gravitational lensing in particular, you need to get redshift. And you need to get the redshift of the sources in order to decouple gravitational lensing effect from intrinsic alignment of galaxies, and to decouple the cross correlation that you may have between gravitational lensing effect and foreground galaxies and the shapes of foreground galaxies. And this cannot be done if you do not have enough information on the redshift, and not only for lensing, but also for intrinsic alignment, which contaminates the lensing signal. So to do that, Euclid is not enough because getting photometric redshift of billions of galaxies requires a photometric redshift by adding, in addition to photometric surveys, optical data that will come from ground-based facilities. So the Euclid surveys itself is a combined survey that uses space missions and ground-based missions. And I think that it's an important point to keep in mind is that all next generation surveys will no longer separate space mission and ground-based mission. It will be integrated surveys. And that's a key point to think about for the future because it impacts also on the strategy prior to select a mission is what it will be the impact for the ground-based facilities. It is true for Euclid, but it is also true for Plateau, for instance, that will have a huge spectroscopic follow-up in order to monitor this planetary system and the stars associated to planetary system. So that's a key point certainly for the future to keep in mind. The coupling between ground-based and space-based observations that will be really strongly coupled. So these photometric redshifts will be used also in order to find clusters of galaxies, and we expect between 50,000 to 60,000 clusters found by Euclid that will be obviously analyzed together with our Eurosita data. So the Euclid survey is a big machinery that will use a Euclid satellite in order to get high image quality for weak lensing measurement down to 24.5 AV 10 sigma for the measurement of the shapes of galaxies, a near-infrared photometry in 3 band, and a slitless spectrograph that will measure emission line galaxies in order to get spectroscopic redshift on a subsample of about 50 to 50 million galaxies. So in order to use this weak lensing analysis, you need to couple with external photometric data from ground-based and a spectroscopic follow-up in order to calibrate the photometric redshift. So you see how coupled the ground-based and space-based observations are in this kind of missions. And Euclid is basically, a power spectrum machinery that will get the power spectrum of galaxies and the power spectrum of dark matter as function of look-back time. And when they are coupled together, in addition to Planck data for the priors for the analysis of the cosmological parameter, then you can recover information on gravity, dark matter, and dark energy. Of course, because you will have billions of galaxies and billions of redshift for those galaxies, this mission has a huge legacy value. And I think that's important for all these missions that use huge resources, that the legacy value is an appealing aspect of all of them. That means that all these data should be public as soon as possible, because this data does not belong to those who are doing the surveys. They are belonging to the European community or the US community when you are using agencies to provide all these facilities. So the Euclid mission itself has been selected in October 2011. It is fully funded by at 2/3 level by ESA and the rest by national space agencies. It's a mission that will have a 1.2 meter telescope, which is in silicon carbide, and a 3-mirror anastigmat telescope, and that's a concept which is also used for WFIRST and Castor. So it really is a next generation, so extremely stable mirror, with 2 instruments, a wide field imager that will have roughly the image capability of a Hubble Space Telescope, but a 0.5 square degrees field of view instead of few arc minutes. And also a near-infrared wide field capability for near-infrared photometry in 3-band, and a Grism slitless near-infrared spectroscopy that will cover the range between 920 nanometer to 1850 nanometer using 2 sets of Grisms. So the observations will be done in parallel for the spectroscopy and the wide field optical imaging capability. So the downlink is 850 gigabit per day, which is quite huge, and there needed new development from ESA in order to be able to download all these data sets. And the ground segment is a huge part of all these surveys, not only Euclid, it's also true for WFIRST and probably Castor as well. We expect about 100 to 300 petabytes of data, all including the ground-based facility data together. So the satellite will be in L2 orbit as Gaia, Planck, or Herschel. It will be launched by 2020 if we have no delay, and I guess we will have delay, but at least that is the current deadline so far. And the mission itself is expected to be done in 5 years. Okay, so it's 625 years predicted here, but the survey is scheduled in order to be done in 5 years. Okay. And the motivation, the design is really driven by weak lensing. So this is a telescope as it stands now. So the service module here and the panels are developed by Thales Alenia Space Italy, and the telescope is developed by Airbus Defence and Space. The detectors are provided by E2V for the optical and Teledyne for the near-infrared. And the instruments which are located underneath the telescope here are the near-infrared spectrograph and photometer here, and the wide-field optical imager here. So this will be the biggest near-infrared camera ever done so far for space, and this is the second biggest camera ever done after Gaia for the optical. Okay, so it's the detectors here are E2V CCDs, improved as compared to Gaia. It's next generation E2V CCDs, with in particular optimized for low red dot noise in order to correct with sufficient accuracy, the charge transfer inefficiency produced by the degradation by cosmic rays of optical detectors. Okay, so the instruments are developed by a consortium of about 120 laboratories in Europe and the US, and they are delivered to Astrium, to Airbus, and the telescope is delivered to Thales. You know, the hierarchy is the following. So the main contractor of the whole spacecraft is Thales Alenia Space Italy. Okay, so the image quality we expect with Euclid tells us where is, you know, the future and what we expect in terms of revolution. This is a simulation of M31 as it could be seen by the Sloan Digital Sky Survey at redshift 0.1, as it will be seen by Euclid, and as it will be seen by Euclid if it were at redshift 0.7. So you clearly see that the image quality, and that means the morphometry, is a full scientific objective of this next generation space survey. Okay, and the goal is really to provide the equivalent of the Sloan Digital Sky Survey, but instead of doing that at redshift less than 0.05, you are going to do that at redshift 0.7 or so. So it's really an increase of volume, and the descriptions of the universe with the image quality of nearby surveys, but at redshift about 1. So to some extent, because of the spectroscopic capability, in addition to the imaging capability, it's a kind of super Sloan survey for the future. So in terms of the potential for gravitational lensing for dark energy analysis, here you have an estimate, a prediction of the growth rate of structure as it will be seen by Euclid using only spectroscopic data and not weak lensing, okay? So this is a growth rate, and here the growth rate times the normalization by the dark matter power spectrum, sigma 8. The points here are the current data set we have so far, and here these points are those you expect with only 20% of the spectroscopic redshift of Euclid and no weak lensing information. So you see that the potential in terms of, you know, discriminating, you know, dark modified gravity model and dark energy model is really quite impressive. And in fact, in terms of improvement, we are close to 50 to 100 as compared to current estimate we can do so far. Okay, so now in terms of the estimation of the dark energy equation of state, which is characterized by a constant term plus a term that may depend on time. This is the current estimate we have today on W0 and WA here, using, you know, all the surveys and Planck. This is what we expect with Euclid weak lensing, Planck and baryon acoustic oscillations here. And this is what we expect when we include, in addition to weak lensing, galaxy clustering coming from the redshift surveys of Euclid. So in terms of figure of merit, that tells you, you know, how well we can do in terms of accuracy in the measurement of the parameters characterizing the dark energy or modified gravity. You see that the improvement factor may be as high as 40, for WA and WP, simply because of this image quality that kills, you know, the systematic residuals, which is a key point for all these kind of surveys. So in addition to that, we also have the legacy value of these instruments. And of course, the key issue here for the major point for this kind of surveys, not only Euclid, but also WFIRST and Castor, is the fact that you have a very large number of galaxies and stars with a huge diversity of population that you can explore by subsamples. And you also, because you are exploring a huge part of the sky, you also have, in addition to huge number and huge volume, you can also have access to very rare objects. And the rare objects in particular concern the very high redshift quasar, for instance. Okay, so the number of very high redshift quasar at redshift 8 or higher than 8 for Euclid is about 10 to 20. Okay, that to give you an idea of what to expect. All these points, and in particular providing targets for next generation facilities is also a key point for this kind of next generation wide field optical surveys from space. So one example, I think, which really express how far we can go is to see, the SLAC survey, which shows, strong gravitational lensing around galaxies. This is, so far, the best strong lensing cases we have around galaxies obtained with the Hubble Space Telescope. Okay. And this is what we are going to obtain after 2 months of Euclid, and we expect 60 months of surveys. So you see that only for this kind of science related, to probing the dark matter distribution around galaxies using Einstein rings and arcs, for instance, is really a huge improvement with respect to what we could do today. So then you can split the samples into by redshift, by morphological type of galaxies, and so on, and explore, all this using, the pure gravitational lensing effect without assumptions on the dynamical stage of the galaxy itself. W first, so it's a near-infrared facility with a 2.3 mirror class telescope, also 3 mirror and astigmat, as for all this wide field image capability. This telescope will be equipped with 2 instruments, a wide field instrument, several instruments, not 2, a wide field imager working in the infrared with a rectangle shape field of view that will cover about 1.3 square degrees, roughly the same as Euclid, with an integral field facility, which is really quite different from Euclid, which has no facility, such facility. We'll have also, in principle, a coronagraph. It is under study for the moment. There is no, it's not demonstrated that there will be a coronagraph, but I think that the revolution for W first is there. So I think that it's really, really important to have this for this kind of telescope. Okay. It's also planned to be launched by 2024 for a 5-year mission, and as compared to Euclid, which is a pure survey, it will have 25% of GTO time. So anyone could make proposal in order to get time on it. So the main survey will cover 2,000 square degrees as compared to the 15,000 square degrees of Euclid. So it's rather something which goes in between very large field of view and very deep, which places W first in between Euclid and James Webb Telescope to some extent. Okay, but the 2,000 square degrees means that you can probe the large-scale structure at very high redshift, and the drivers are dark energy and exoplanets. So for the dark energy, in addition to as compared to Euclid, W first plan to have a supernovae, type 1a supernovae survey that will use, the IFU in order to get the redshift, but also extremely accurate photometric data. Because the key point in order to beat the systematic for type 1a supernovae in 10 years from now will be the systematic residuals on the photometry. So in addition to that, because it will have imaging capability in the near infrared and also slit-test spectrograph, it will also explore galaxy clustering through the baryon acoustic oscillation and redshift space distortion, and with lensing using near infrared imaging, which is something new with exploratory. It's a new territory because pixels in the near infrared have not the same performance nor the same characteristics as E2V detectors. So it is something new to explore. And in addition to that, it will also have a microlensing survey and a high contrast imaging capability with a coronagraph in order to detect planets. And you see that it is expected to find 3,000 cold exoplanets and 300 Earth mass planets with this kind of microlensing survey. And here, with high contrast imaging, it will also explore, planetary systems and stars and dust around stars in order to see to characterize this, planetary formation system, which is really a new territory as well, which will be unique for this kind of capability. So, in terms of depth, it's really different from Euclid. Euclid goes to 24, 24.5. The goal here is to go to 26 to 25 to 27, depending on the types of surveys you are going. So it's really intermediate between Euclid and the James Webb Telescope, with special facilities in particular for exoplanet. And I think that this coronagraph is really the key point. Castor is a new concept, which is proposed, is not funded yet. It's a proposal made by Canada in order to build up a 1 meter class telescope, also in SIC and a 3-mirror anastigmat, wide field imager, also a field of view which is very similar to Euclid and WFIRST, with 3 filters covering the near UV down to the, up to the optical wavelength range, a slitless spectroscopy, and an image quality which is also similar to what you expect for Euclid. Okay, so the concept is really to focus on the near infrared, on the UV, in order to provide external data that will be used together with other facilities. So the depth they expect with the 3 filters here that will be done in parallel is really to go to 25 to 27 as well, with a wide field survey that will cover 5,000 square degrees of the Euclid sample. Okay. Now the key question here for the future is really the complementarity and the synergy of all these surveys. Euclid is typical in this respect because it will use optical data from the ground and spectroscopic calibration for the photometric redshift that will use ground-based data and space-based data. So for the photosyn, where the DES, CFHT, and LSST will be used, and the calibrator for the photometry and astrometry will be Gaia. For the ground-based facilities, it will use, for the spectroscopic calibration, it will use DAISY, FORMOST, MOONS, possibly PFS and MSC, which is a next-generation telescope for CFHT that will be dismounted in order to build a 10-meter class telescope, if it is funded. And all this will be used together to create the Euclid survey. Okay, so you see that the Euclid survey is not only Euclid; it's really a fully integrated project. So now, if you compare DAISY, LSST, Euclid, and WFIRST as the next generation surveys you can expect that will use broadband filters from ground-based of space. You see that most of them will cover several thousand of square degrees, with typical field of view, which are half a degree for space mission and 10 square degrees for ground-based facilities. And all these surveys will accumulate, spectra and imaging capability for several millions of galaxies. Okay. And they will be used together. In particular, LSST, Euclid, and WFIRST are really complementary data sets that will be used together. Castor, if it is done, will provide extra data with the same image quality as Euclid and the Hubble Space Telescope in the UV. And that's something definitely new, which will provide strong improvement in terms of photometric redshift. So you see here, Euclid and LSST, Euclid and Castor, Pan-STAR, Euclid and Castor, and here LSST, Euclid and Castor. So this is the improvement in terms of stability for the photometric calibration. Photosyn is a factor of 3 to 4 when you use together Castor, LSST, and Euclid. So that's a comparison of what you could expect for these 3 space-based surveys that will be roughly launched almost at the same time. This one is still under the discussion. It's not funded at all, so it's still a project. But will provide something unique in terms of UV capability. So If you now dress a profile of what could be, the next generation wide field space-based surveys, it's definitely multi-wavelengths, multi-mode, that means morphometry, astrometry, photometry, and spectroscopy together with imaging capability. The synergy between ground and space is definitely something that will be used for all these surveys. All will have HST-like image quality, and that's really definitely the goal. You use HST as a baseline to build up next generation all sky surveys in the optical. And all are big collaboration that will be used billions of sources. So the computing resources, which has not discussed it, is really a key issue for this survey. So in terms of last point regarding this survey, and I think Massimo will be happy with that, is that all the survey must be thought integrated, ground and space. It's impossible to do that with one single capability, okay? And they are complementary. This is W first Euclid, W first Castor and Euclid, Euclid plus Erosita, and Euclid plus LSST to some extent. Thank you very much.
Thank you, Yannick. We have time for a question or two.
I take your point very much on trying to get all these facilities to. I take your point on. Does that work? No, sure. I take your point on trying to coordinate all of these big facilities, and I agree it's extremely important. If I understand it correctly, I think the Euclid deep field is quite far south. I'm not sure if I'm right on that, which means it may not be in the right place for MSC. So do we persuade Euclid to move north, or do we persuade MSC to move to the southern hemisphere?
Okay, so for the deep, you mean the deep surveys, Euclid deep. Okay. So actually, the Euclid will have two deep surveys covering 2 times 20 square degrees, one in the north and one in the south. And one motivation to have one in the north is, in particular, to be able to use these facilities we have in the north, CFHT, MSC, and probably Subaru, in order to cover this with these fast facilities. The north is much easier, the south is much easier, of course.
Even better would be to have a field where we can have SKA and MSC and Euclid.
That's correct.
The way at the moment is we either have SKA overlap or we have MSC overlap, because Euclid, I think, struggles to get the deep pointing in the equatorial region at the moment. Right?
Yeah. Well, we have a constraint regarding this one. The two fields are not defined yet, okay? So we still have rooms to change this. But we have also, constraints coming from the operation of the telescope itself. And because it moved, from the north and after 6 months to the south, and you need to have repeatability of the position of the deep field in order to use them for calibration purposes, we have strong constraints in order to define them. So having something that could be common to the 3 facilities is not sure yet. And we cannot guarantee that simply for operational reasons. Okay, but for the moment, they are not defined simply because we are waiting for a better understanding of the telescope and see whether we can move the deep field to something that will be visible by all these facilities together.
One more question.
So is the accuracy of photo-Z for weak lensing just for Euclid going to be achieved even if Castor is not founded? Because when you show the plot of the photo-Z, the gain in accuracy wasn't clear to me, actually, considering that you are adding the ultraviolet, and
yes.
Castor was coupled with W first. But in case Castor is not founded, are we sure that the threshold below 1?
Yeah, because yes. The main issue, the photometric redshift for Euclid are mostly driven by intrinsic alignment contamination and not by the DLS over DOS term coming from lensing. That means that the accuracy we need for the photo-Z is not 3%, it is 5%. Because of that, we don't necessarily need the UV. So the requirement in terms of photo-Z accuracy and outliers fraction is driven by that number. So in principle, we don't need Castor to meet the requirement of the Euclid wake lensing science. Okay, it's a huge improvement, definitely, and it is a nice to have in order to improve even the cosmological parameters we can derive from it. But in terms of requirement, 5% plus 10% outliers can be used if you have 3 bonds in the infrared plus 3 to 4 bonds in the optical without a UV.
Well, thank you very much, Yannick. I think we have to move on. Moving on to copy. And can I ask you to be back at 11:10, please?